Hello and welcome to MIS 769, week 5. I get everything right here. So, let's get started. Without big data, you are blind and deaf in the middle of freeway. I don't know, I love that quote. I just do. And I just saw today Databricks got a $5 billion, I think it was $5 billion, some outrageous amount of money investment in it. And it's because we're at a point where we can take big data and actually do something with it. To really kind of time in the last, I don't know, maybe 5 years, we've really been able to take this huge chunk of data we've been collecting and now do stuff with it, process it, get intelligence out of it. Not just real simple stuff, but really dig in and try to figure out what is the data telling us. So this is this chapter or this kind of lecture is going to be all over the place, and I apologize for that. That's just kind of the way it falls, because I've tried, shoving a bunch of stuff in the last chapter or last week's lecture, week 4. Just too much. Even this is a lot for some students to take in. So let's go into bag of words and TF-IDF. So let's actually, I think I had a better picture. Oh, there we go. The bag of words is basically just this. It just counts all. I'm gonna go back here. Basically, just counts all the words. Maybe if I can go back. Well, that's better. I had some weird. I've been having weird internet problems all day today, so hopefully my internet doesn't drop. So bag of words is just distributional words. I is there in that sentence 5 times. The is 4 times. It's really quick and it can be useful for certain things. Yeah, we'll just leave it at that. It's just basically a distribution of words. Now, TF-IDF. So you're looking at the term frequency and the inverse distribution. So I have a description over here. Basically, what we're trying to do is get rid of like the I, the, to, all the words that are just relatively common, and keep rare words or more important words, especially if they're spread over multiple documents. So if we look, the cat sat on the mat, the dog chased the cat, the bird flew over the mat. The word cat appears in document 1, document 1 out of 6. 1, 2, 3, 4, 5, 6. And it appears in the other ones 1 times 2, 3. So the IDF, you get this calculation of 0.29. Now the word the, 1, 2, 3, 4, 5, 6, I was just say 3 times, doesn't really matter. It appears in every document. It basically cancels itself out. Okay, cat retains some weight because it appears in only some of the documents. The IA gets basically weighted out or destroyed or zeroed out. It's divided by 0, and that way we can try to understand what words are important. Now, TF-IDF is still used a lot, and we use it to try to find, certain syntax, certain words, certain things we're looking for that might not be common in every call transcript, every text document, every chunk of data. And it's not that necessarily you're looking for the outliers. It's just you're trying to figure out how that document and that word are related, or what documents in that word are related. Okay, now when we talk about bag of words or a lot of other things, there's a lot of problems. There's lack of context. Words are treated independently with no understanding of relationship. Cat and kitten are 2 completely different words. They're not related in bag of words. It's just a distribution. High-dimensionality, 1 dimension per unique word. Vocabulary creates a massive sparse vectors that are massively memory intensive. So if you were just to go through and say, hey, here is a word, and I'm going to make a dictionary entry for it, you get a lot of dictionary entries. You get a lot of, 1, 2, 3. If you just take the first book you read and just say, hey, here's all the words, it creates a problem because we have just count was too high. Fixing vocabulary. New and especially misspelled words. Previously unseen words are simply ignored or dropped. Again, there's no semantic meaning. Words are purely statistical counts. And we'll cover about how to fix that. And like I said, I know this is kind of a weird introduction, but it's just kind of the way things have kind of happened over the years from teaching. When we create a model, or when we create a machine learning model, when we actually create a neural network on a machine, we can save it as a pickle, a safe tensor. There's a couple different formats, okay? And pickle, it used to be a more popular method of saving a brain, a computer brain, a model, okay? Now we've moved on to a safe tensor, which is a little bit better because a pickle can have arbitrary code execution. What do I mean by that? It means I can send you, okay, you know how like when you have an Excel file and you open it up and it says, hey, this might have bad code in it, might have VBS in it. Well, a pickle can do the same thing, except it might not tell you. So you have a pickle file, literally just a single file, but I tell it, hey, send me all your passwords. That would be bad, okay? So when we start thinking about text and corpuses and models, we have to think also too about the source incoming data and what we're going to save it as in the outcoming data. And a pickle is just, and I'll talk about safe tensor next, I think. But it's just one of a format. So, when we talk about these models, I'm sure most of you are familiar with CSV or XML or Excel documents. Some other ones are, JSON, Parquet, which I use a lot. You save an SQL file. But when we create these models, pickle is just an older format. And like I said, the problem with the pickle is you can put code inside, you put Python code in it to execute, and when it executes, you can do something bad. So we don't really use pickles anymore. We use safe tensors. Now, a safe tensor is just basically it's just a list of tensors, okay, a list of numbers. Okay, I'm working on a project where I'm trying to measure a person's smile. The smile. With Parkinson's, Alzheimer's, stroke, ALS, frontal temporal dementia, and a bunch of other diseases, they lose the ability to smile. Okay, and if you think about it, when you drink alcohol and you get really drunk, you lose the ability to move your face. That's what your brain does, and without full function, full control, executive control of your brain, you can't smile and be sad, and you can't emote as much. So now, if we think about this, I can send a video of a person smiling, but now what's the problem with that? There's privacy information there. I can see the person smile. I mean, I can see his face, and they're smiling. That get out on the internet, that could be bad. They may not want that. That would maybe be more like a pickle, a bad format. A newer format would be a safe tensor. Now, a tensor is just a mathematical vector, I guess would be one way to think about a mathematical number. Okay. Now, if I could have that person smile and say, hey, he smiled 12% higher than just baseline, just say 12%. The next person smiles at 18%. The next person smiles at 15%. Just keep those numbers. It's very safe. I'm just keeping numbers. I don't know who they are. Okay. That's what a safe tensor is. And it's inherently a better format. Okay. You go back to, the other thing, CSV, you can't put code in there to run. Excel, you can put code in there to run. Excel, you can I can send you an Excel file and it says, hey, do you want to run this file? And you hit yes, and the VB script or the VBS script just steals your passwords. CSV doesn't do that. Much like pickle and safe tensor. So just kind of keep that in mind. Okay, so data frames. And I guess the best way to think of a data frame is just like an Excel document or CSV. It's rows and columns in the computer, and not necessarily something you can always see. Today, I was working with something that was 11.7 billion rows, or with 20 billion rows, and I deleted 11.7 billion rows. There's no way that I could really open up, 20 billion rows and delete, 11.7 billion rows. This was for 3 months worth of data too. So But I know the data is in columns, and I know each column has a row. It's like Excel, and that's really what a data frame is. The difference is that it's not really, you can't necessarily always see it the same way, but you can on a data frame say, hey, I want an average of this column. I want an index. I want to do these type of things. So that's literally what a data frame is. When people say data frame, and it's kind of one of those weird things because sometimes when people talk about an Excel file, they might be talking on the Mac about numbers or Google spreadsheets, Google Sheets, I guess. And so it's kind of like, like Kleenex. It's kind of a nebulous term. Are you talking about the exact brand Kleenex? Or are you talking about just facial tissue? Same thing with data frames. Are you talking about a Pandas data frame? You're talking about a NumPy data frame. What is Spark data frame? There are differences. So I just wanted to cover kind of what a data frame is. And basically, when you hear me saying a data frame, or hear other students say data frame, just like kind of like a CSV online in the computer that we can process. In terms of big data, a lot of times we'll talk about a Spark data frame or a Pandas data frame. Okay, regedit. Okay, regedit is kind of like a programming language, and also kind of like SQL. SQL is kind of a programming language. Now, what do I say that? Because SQL, there's TSQL, there's MS SQL, there's all these different, there's MySQL, there's all different kind of flavors of SQL, and regex is kind of the same way. Okay, so regex is an ability to search using expression, using a method in either a data frame, a table, a column, some way you have data and you want to search for something. Now, regex is, I don't want to say really popular, it's really fast, really nice, and it can do some really crazy stuff. I use regex all the time. Well, also I use it every day. I have a couple regex commands, and I just run them, and I don't need to change them, and they work great. Because regex on very, very large data is great. Now, the problem is writing regex before ChatGPT sucked. It was just absolutely horrible, and I'm not a regex guy, and I use it all the time, but it's difficult for me. So now, what are some really nice things you can do on regex? So if I have 11.7 billion rows, like I said, like I did an hour and a half ago, if I want to rip out all the emojis, I could do that relatively easy. I noticed that on like one slide back, 2 or 3 slides, I have these double dashes, which I hate. Okay, and somehow I had a semicolon, but when I copied it into my PowerPoint, it became 2 dashes, and I don't know why. In regex, that'd be super easy to change. Okay, so regex allows you to search for and find and even change text more or less very quickly. We can search for text like a similar method, like a find, or we can use regex. Regex is generally always preferred over a find because it's generally faster. And we're talking big data, and again, it's hard because big data is something different to everyone. Maybe 1 million rows is big data. Anything outside Excel might be big data to you. To somebody at a bigger company or working on bigger projects, 11 billion rows might not be that big, and it's like 280 columns wide. And my project was to take 3 hours. It basically takes 3 hours to run the code. I got it down to 43 minutes. So that is, that is because of optimization. If you think about it, if code takes 3 hours to run 5 days a week, that's 15 hours versus 43 minutes, which is, I don't know, less than 5 hours. It's like 4.5 hours, 4 hours a week. So I just saved an employee 10 hours of time. Figure an employee, or that cost might be $100. So that is, I don't know, $1,000 a week, $50,000 a year, by just spending an hour or 2 of my time optimizing code. And really, honestly, 20 billion rows is not a ton of data. It's like I said, it's like 3 months of data, I think, 2 months worth of data. Because today is February 6th, well, it was to February 6th, today is February 9th. So I think we're running it might even be 2 months worth of data. So regex, like I said, is just a method to search for text and non-text characters really quickly. And again, I'm sorry this is all over the place. I know it's just the nature of this course right now. Because we cover very structured stuff, and then we kind of cover all the other things that either certain books don't have or certain materials don't have, but you need to know what they are. And why is NVIDIA so popular? Why is it such an expensive company? What do they do? At the end of the day, what does NVIDIA do? It's not really a fair analogy, but what does NVIDIA do that a computer can't do? So, GPUs, computers, and I actually got a video code right here. So, almost have the same thing. I have a 2070 right here. Okay, so a GPU. You have a CPU, which I don't happen to have any handy here. You have a CPU, and then you have a GPU. What is the difference? Fundamentally, what is the difference? Well, a CPU is a master of all. It can do a lot of different things. It can load Word. It can, I don't know, play games. It can do, it's also like K-pop. It can play K-pop from YouTube. A GPU can't do that. A GPU, at the end of the day, cannot do that. A GPU is a very kind of expensive matrix math machine. It takes numbers and multiplies them really, really fast. Now, my machine here, I think, has 8 or 10 GPUs and cores in it, or sorry, 10 cores, so 10 worker bees. Okay, so if I give it an instruction, it can spread out between 10 workers. Just like we learned in MapReduce or in other things, that often CPUs have about 10, 20, 30. Some of the higher end machines have 100 some cores in it. Where GPUs, can have many, many, many more cores, thousands of cores. Okay, but again, they're very limited in what they can do, and they're just designed to do a certain type of math that helps with deep learning, that helps with machine learning. So that is why it's so. That's why GPU is so, important. Now we covered bag of words and some things like this. So now we're kind of circling back. So what is a vector? And it's hard because I've gotten in trouble for saying the wrong thing here. So not all vectors are embeddings, but for this class, we'll consider all vectors embeddings. So a vector, to me, is just a number, like a direction and motion, or you're going 55 miles per hour south by southwest. You're going 80 miles per hour east. Okay, to me, that is what a vector is. It's just magnitude and direction. Okay, but now, what vectors give us? Okay? Vectors give us relationships. Okay, vectors give us relationships. When we have a bag of words, we just have a distribution. We just have a count. We know the word I was in there 12 times, but we don't know if I and me are similar. That's where vectors change. Okay, vectors give us relationships. Okay, and I have some more stuff here, but not really worried about. So, if we think about this, you shall know a word by the company it keeps. What does that mean, Richard? That means that if I'm talking in finance and use the word bank, it's a very different set of words. Corpus is a different dictionary than if I'm talking about a memory bank. Okay. This GPU has a VRAM bank. I mean, it might have, I don't know, 4 banks of RAM that account for 8 gigabytes. That's the total amount of VRAM in this memory bank. Okay, I'm missing my credit card. That's not good. My bank account, I get paid tomorrow. I get paid Wednesday, I guess. And my bank account will get funded. They're both the same words, but different contexts. So that's what that means. Now, I put a picture of a highway on here. Why? Well, let's see if I have it on the next slide. I'm pretty sure I do. Because the way I really learned about vectors, the way I think about vectors is, when people head to California, when they get from Las Vegas and they start heading to California, we know they have certain things in common. We know that they're heading towards California. They might be Californians. They might be San Diegoans. Dalgons, as Ron Bargan would say. They might be Los Angeles. They might be Santa Barbara. They might be heading to San Francisco, but they're all kind of Californians. They all have some similarities. They have to pay, personal income tax. They all have to pay certain vehicle gas tax. And when people go up to Elko, and they might be stopping at Ely, or they might be stopping at Wells, Nevada. I think of my geography up there, and they have a certain set of similarities. Much more likely that people working in Elko and Ely are miners. Not all of them. They're waitresses and computer techs and everything else. But a lot more chance that they're miners than people driving to San Diego or LA. We can kind of cluster these similarities. And that's why vectors are important. Because if we kind of know the direction of a word, kind of know the direction of a person, a car, the direction they're heading, we can kind of make similarities. Pinecone is a vector database company. I have a real good little graph on it and a real good little talk on it. Oh, I did not. Did I put it in here? I didn't. They have a couple pictures about vectors that might help. So I believe that's hot linked. You can just click on it and go there and read that. I'll see if I can post it on the talk, on the additional reading. But, when we think about it, we have Richard Young and Rick Young. Well, in bag of words, that's two different things. We also have Richard Young, but he was born in New York and currently in Paris. So how do we group these two together? How do we kind of cluster them all together? And that's why vectors have become so important in NLP. We can show semantic similarity. Even though Rick and Richard are different, we know that they're heading on the same road. We can enable machine learning models. We can understand contextually things similarly. So I think this one might be from, it might not be, I don't know. But you can see here, king, man, woman. The vector is all kind of heading in the same direction. And I know it's kind of an oversimplification. Apple, banana, orange, they'll kind of cluster over here. Football, golf, tennis, they all kind of cluster over here. Okay. That's basically where you get vector. Now, word to vector was one of the first word to vector programs. 2013, I thought it might have been earlier than that. But it was basically taking literally a bag of words and converting them into numbers. Now, there were some problems with that. We really didn't understand similarities. We didn't understand everything. We didn't have an embedding. Each word there would have a single vector, regardless of its context. Word, vector. We have one word to the vector. We don't know about its friends. We don't know about the words it keeps. We don't know what else is around it. We know that this word has this vector. We don't know what else is around it. We don't know how that word changes. Where transformers comes in. And here's an example of that. This is word to vec. This is where we have to have vectors. I ate an apple for lunch. I bought an Apple MacBook. You're the apple of my eye. So all three of those words would have the same vector. They have different meanings. The embeddings would be different. And while they all have the same vector, we're still missing that context. That's why, 10 years ago, coming up real close in 10 years, when we talked with a chatbot, we talked with Clippy or other things like this, it didn't always understand our questions. So it's starting to get cold out of some clothes. So anyway, so when we do word embedding, we generate a different vector related based on the words around app to give it context. This is exceedingly important because we may not realize it, but so often in English, especially in domains, we use words differently than, I don't want to say, non-domain specialties, but it's true. Cyanosis, which is like small, is used in cardiology different than it is used in nephrology and in different parts of the anatomy. In neuroscience, we use terms differently. In computers, we use terms differently. And so having a model or having a mathematical way to be able to understand the context of the words is extremely important. And I guess in some ways that is what fluency of a language is. When people first learn, I guess, English or other languages, when Americans first learn Chinese or French, understanding the correct use of the same word in different contexts is important. And so that's literally what contextual embedding is. It's understanding the word in its context. And there's a ton of different embeddings. Here's just a few of them. So when I say context independent, like right here, we have word embedding, we have context dependent, and we have context independent. And the word to vect is context independent. Fast text love, emo is really one of the first ones that was context dependent. So what happens when we say context dependent means we look at the distribution of the words around it to understand it. Here's another example. I think this is one maybe from the Pinecone. Cheese loving mouse, fast moving mouse, click the mouse. They're all kind of different contexts. So that's where we get into the dependent, context dependent. And really you have RNN, which is kind of an older style of a recurrent neural network. It's an older style of understanding words in relation to each other. There's a lot of limitations, but this was really the first one. And then that famous paper, context is all you need, or attention is all you need. That's what basically started the whole transformer network and got rid of recursion. Ooh, let me go back. Now, we need to be able to save these vectors in a database. So the issue is vectors are really long. Let's say they're, I don't know, 1,000 numbers long. Sometimes they're long, sometimes they're short, sometimes they're, all over the place. Standard SQL databases, standard databases don't store them efficiently, don't search for them efficiently. They're not designed to do that. How are most databases designed? Well, there's really kind of two types of databases. We know this. There's SQL style kind of tables and columns type database, and there's no SQL database like the JSONs and semi-structured data. There's things like that. MongoDB is an example of one. Well, for storing vectors, neither one of these are really the most efficient method of doing it. So there's a new type of database, vector databases, and again, just like with regular databases, don't get hung up on that it's some big computer. A lot of times, like with that FASS, FAISS, you can run that on your local machine. You don't need like a different server. There are other local databases that you can run on your local machine for small models. I have a project where I'm looking at papers and I want to find papers that are similar to this. I use a little local vector database. I also have a much bigger project where I'm storing full books, trying to understand certain things. I use Pinecone for that. So they're just basically ways to store vectors. So what happens is you have text, a book, a paragraph, a document. You embed it. And so when I say embedding, here, when I say embedding, what I'm doing is I'm going through that book and converting the words into numbers. I'm vectorizing it. I'm also kind of encapsulating the word to round, or at least understanding the word to round it. So apple looks at, you know, the of my eye, of looks at apple, my looks at everything around it, and embeds it. And then since I don't want to have to do that again and again and again, I save those embeddings into a database, those vectors into a database. So like I said, over here, I'm, I don't know if I've ever honestly used that one, but the Facebook, the FAISS, I use that all the time. Pinecone I use all the time. Like I said, what those are just basically ways to store the vectors that you embedded, the vectors that you created. And why do we do this? Because one of the best search methods, or one of these search methods that we use, is cosine similarity. And I know I cut this off. I just want you to understand the idea of cosine similarity, and basically the idea of, hey, people kind of on the highway to California, they're all kind of going to California. Now, they may not all have the same destination, but the further away the cosine is, the less likely they're similar. If a car is heading to Elko, which is, I guess, up north, and a car is heading to California, which is west, the distance between those two vectors, the direction they're traveling, is greater. Where two cars heading in the same direction, their cosine similarity is closer. And so, since their cosine similarity is less or closer, they might have more in common. So one of the ways we do this embedding is we tokenize everything. And there's a couple different ways to tokenize it. But basically, when we talk about tokenization, what we're talking about is simply taking each, do I have an example of it? I do. We're basically taking each word and breaking it up and then converting that either into a number or some type of unit that the computer can process. Okay. Then we have to figure out, like from the last lecture and also this lecture, do we want to remove any words? Sometimes removing words can make things much more efficient, but also it can make things less clear. If we remove the word not or of or the, it can dramatically change the meaning of a sentence. So this is from the book. And you see how we tokenize it into each one of the words. So we break down text into smaller chunks, okay, or smaller pieces. And then from there, we do the embeddings. We turn the tokens into numeric representations. There's also, this is word tokenization. There's also sentence tokenization. There's a bunch of different, sentence embedding. There's a bunch of different methods to do this. So this is just a very generic method right here, but it's very common. Sometimes some systems use like a fixed word length. Some, do it on a white space. Some do it on a comma. Every system does it a little different. Whole words, apple. Parts of a word, app or e, and characters, punctuation marks, special symbols. This is how you would take that word or that sentence or that text and chunk it or tokenize it to convert it over to a unit that we can now vectorize, we can embed. Like I said, there's a couple different ones. The more modern one is byte token. But word token, earlier like word-to-vec style tokenizations, where each word is treated as a unique token. And we just look at the white space, boom, done. White space, done. Subword token. The most common approach where words are split into smaller subwords. Okay. Character tokenization is super fine grained at the character level, which can handle new words, but may face challenges with efficiency. So again, you're working on each individual character. So, byte token, instead of feeding it words, we send it individual bytes, of data. Now, the reason we do this, or the reason it exists, is because the emoji problem I was talking about. When people leave emojis and notes, there's, that's not really a word. So how do you deal with it? So that is an ASCII byte, right? I don't know if it's an ASCII byte, but it's it's a token, it's a byte. You can convert it over into a character. There we go. That's right, character. And so with byte token encode or byte token methodization, you never have anything that's really out of context, like with traditional word tokens or character tokens. You never have it. It works on all languages. It works on emojis. It's better for probably misspellings. It's better for a lot of things like this. The problem is when you break down everything to a byte, it's super long. It's super heavy, very dense. So it takes a little harder and it's longer to train on a byte level token than other methods. Use like a T5 model. I don't know, I'm trying to think of some other models that use byte level tokens. That it takes longer, but it can. I don't like to use the word. It can do more. It can understand more universal languages. It can understand emojis. It can understand context sometimes more. Context means different languages or different emojis or misspellings compared to other token methods. So that's and those are just some of them. There's a couple more I can think of, but those are the major ones. Everything else is kind of like a subcategory of that. So the demos I will record separately. I think I have actually here. You know what? Actually, no. I'll put them on here. So I have two demos for this course. Let me get them queued up. This demo used to work a little bit better, but things changed. I can share this if you guys are interested. So what this does is, or what I wanted to show, and it works for this, is that you can type a sentence, and I want to show you how it generates tokens. Okay, so feel like dogs, but so that's my sentence. I just want to generate a few tokens after that, and you see next token I, next token, I am sorry. It seems like you're, I don't know why that's that. Let's see what else. Some people like tea, but I prefer coffee. Some people like green eggs and ham. So you can see a new token. It seems that is an incomplete statement. It's not the biggest model ever. This is just a little Microsoft model. Is now a good time so next token yes, next token comma, next token it. So you can kind of see how when we generate the next token, remember we talked about a few different models. There's the BERT kind of model where we mask a word, and there's also an autoregress where we kind of predict the next token. That's literally what this is. So I'll upload this to GitHub. I'll put a link to it right now, and you'll be able to play with it if you want. It's like I said, it will ask you for Hugging Face token. You just hit no. This one does require it does help with a simple GPU. This just is running on T4. But you can change around the temperature, making it a little bit more focused or a little more, I guess focused, or a little more creative. And like I said, it's a really interesting way when you change this prompt right here. I need a few kind of see the next token, and it adds that. Now it has more context, it adds that. Has some more context, adds that. Like I said, I'll put a link for this notebook in the class. But at the end of the day, it's just kind of predict the next token. You actually see that, and with bigger models, and this is the foundational part of token generation. And, we can just build onto this, and create ChatGPT, create Claude. Okay, just wanted to make sure this would run. Here's another notebook. So this notebook looks specifically at attention versus non-attention. So if you remember, we had a slide we kind of broke out to context independent and context dependent embedding. That's kind of what this is. So let's scroll down here. You don't got to, like I said, worry about a lot of this stuff. But basically what it does is it encodes a sentence. The cat sat on the mat. And it uses attention in one method and attention in not another method. So this is the visualization of that, okay? So each word goes through a math formula alone. No words have context or representation of other words. If I was to take a sentence and just mix up the words and just say, hey, read the random words, that's this, non-attention processing. Each word goes through a math formula. No words knows what any other words are saying. It doesn't have any relevance to its friends around it. Now, panel 2, this one right here, the attention weights, that's the middle one here, okay? Every word gets to look at every other word before deciding what it means. Okay, so this is a word. Right here, token is a word. This is another word, token, another word. This is a token, another word. So the numbers, the values, show how much each word cares about other words. So, I guess that's the best way. So, like, if you look here at row 1, everything adds up to 1, but it now looks at the other words around it to understand context. And this is how we apply that. And so BERT is a model that does that. Okay. BERT, is looking at the cat. I think it's the cat sat in the hat, the cat sat on the mat. The cat sat on the mat. Okay, so that's what the sentence we're looking at. I guess it's right down here. The cat sat on the mat. Okay. The bars which show the word summary token, which it thinks matters the most. So bigger bars mean that word is more important to understanding the sentence. Okay. Yeah. So this basically kind of shows, here is a word in isolation. Here is a word in relation to other tokens that the forensic keeps, to distribution hypotheses, and here's how it actually looks in real life. So again, I'll share this notebook with you. Yeah, I know this lecture is kind of all over the place. It's just the nature of it. Let me know if you have any questions. I will do a Analyze Me video. I'll do some homework tutorial videos here in a few minutes. Hopefully you enjoy this. If you have questions, let me know. Other than that, have a great week.